at the start of this section, section 4, think way back, we talked about Taylor polynomials, right? And it was an extension of, okay, we know we can approximate a function with, say, a tangent line, a linear approximation type representation. And Taylor polynomials were just an extension. You keep taking more derivatives and higher powers and keep adding them on. Now, we're ready to make the next jump now to so-called Taylor series. This is what happens. Instead of adding up things and getting a polynomial, yeah, just keep on adding. Just keep on adding. You're adding an infinite number of things together. So we're going to learn what is a Taylor series, how they're useful, and we're going to calculate some. So, we looked at Taylor polynomials a couple of lectures back. And I made the claim back then that, okay, let's say you calculate a Taylor polynomial for cosine x or something, right? I made the claim that if you keep on adding things to your little polynomial, you'll actually come up with something like, well, you will come up with cosine x, the actual function. So this is what today's lecture is all about. Taylor series and also Maclaurin series. Maclaurin series are just a special kind of Taylor series. So what we're trying to do here is represent functions, well-known functions like cosine x and sine x, as an infinite sum of powers of x. And the reason we like to do that is because powers of x are simple to deal with. We can easily differentiate them, we can easily integrate them, and so on. So basically, if we can take something that's, complicated and write it in terms of powers of x, then it would seem that that's a good place to be because we can do things with that simple setup. Okay, so what is a Taylor series? What is a Maclaurin series? Well, think back to the start of this section. We talked about Taylor polynomials. For Taylor polynomials of, say, order, order n, you just had, instead of an infinity sign up here, you had an n, and you would stop there. You would have this sort of polynomial here, and you'd stop. But here, we just keep on going. We're just adding things together. Just keep on going, right? Do we get something meaningful? And if we do we get the function that we're actually differentiating, etc.? Now, a Maclaurin series is very similar to a Taylor series. Let me just, basically A is a point here. You'll see that every time I move from sort of term to term, the derivative increases, the factorial increases, and the power increases. So there's sort of three things that change as you move from term to term. We call this the Taylor series generated by f at the point x equals a. Now, a Maclaurin series is just a special form of a Taylor series, just with a equals 0. So when you refer to a Maclaurin series, you're absolutely saying that, yes, this is the setup that you want. You don't have to mention anything about the point. By a Maclaurin series, you're flagging that the point, you're making a series around the point 0. Okay? Because it's simple. That's a good question. Why are we interested in series expansions at the point 0? 0 is an easy number to work with. Okay? It's an easy number to work with. And if we know something around 0, right, say an expansion for one function, maybe we can shift that graph and come up with other more complicated functions, right? So how do we actually calculate things? Again, notice that as we move from sort of term to term, the derivative increases, the power increases, and the factorial increases. Will you get this in your exam? Unlikely. Unlikely. I'm not sure. I would have a look at the previous couple of can you put it away, man? Can you? Thanks. It must be pretty good. I'll see it later. Will you get this in the exam? Unlikely. Unlikely. Okay, now you may be thinking, where does Maclaurin come from? Well, I'm glad you asked. This is the rather festive-looking Colin Maclaurin. He worked at Edinburgh in Scotland. Now, Isaac Newton was so impressed with Maclaurin that in order to get him, well, he actually paid part of his salary, so that's pretty good. You know, when Newton's bankrolling you, you must be pretty talented, right? Anyway, let's get down to some practical solutions here and see how we can use this stuff to solve problems. Calculate the Maclaurin series for the following functions, sine x. So here, my f of x is just sine of x. Now notice also the wording. We're asked to calculate the Maclaurin series. So in this case, we're calculating the series about the point 0. So how do we do it? Well, you may have forgotten all your Taylor polynomial, etc. stuff, but all we do is look at the derivatives, this function and the derivative. Man, you're in the front row. Shh. Okay? Look at this function and the derivatives at the point 0. That's all it is. Okay? So let's do that. So what I like to do is just have a little table and just form the derivatives in the following way. So the 0th derivative is just sine x. So at the point 0, f of 0 is just 0, right? So now let's go through and calculate the first derivative. So if we differentiate sine x, we're going to get something like cosine x, right? And then just plug in x equals 0 into that. So cosine 0 is just 1. So let's calculate a few more. All right, so if I differentiate cosine x, I get negative sine x. And again, at x equals 0, this is going to be 0. Now, what we're trying to do here, you may think, why are we calculating all these derivatives? What we're trying to do is come up with some general way of writing the derivative at the point 0. So sometimes it's a good idea to write out a few terms to sort of try to look for a pattern. So the third order derivative. Okay, so if I differentiate minus sine x, I'm going to get minus cosine x, right? And I'll do one more. The fourth order derivative. Okay, if I differentiate minus cosine x, I'm going to get sine x. And that's 0, that's 0. Now, can you see a pattern there? Can you see a pattern down the two columns? Well, if you look closely, the derivatives repeat in a cycle of 4. Okay, if you look closely down here, 0, 1, 0, minus 1, 0, then the next one's going to be 1, and then 0, and then minus 1, okay? Down here, you've got sine, cosines, minus cosine, and then back to sine. So there's a pattern going on. What I would like to do is write down, say, the general derivative and the general derivative at 0. So let's try to do that. It's not always easy. Some functions are easier than others for these things. So firstly, let's flag that our derivatives repeat in a cycle of 4. Okay, now let's go into the problem a little bit deeper. Oh, nice hat, by the way. I love it. Is there a story behind it? Okay, all right, cool. I like it. Let's just look at the... Okay, this is important, guys. Look at the even order derivatives. So the 0th order, the 2nd order, and the 4th order. It goes positive sign, positive sign, and then negative sign, positive sign, negative sign, for the even order derivatives. So how can... The even order derivatives are going to be something like this. Now the F2k in brackets, that means the eventh order derivative. Right? So the 0th order, the 2nd order, the 4th order. Let's look at all the odd derivatives. Okay, the 1st order, the 3rd order. It's going to go cosine, negative cosine, positive cosine, negative cosine. Okay, so there's a way of writing that down as well. Okay, so it's going to be something like, pretty much similar up here, but a cosine instead of a sine. Now what we're really interested in here is those two things at x equals 0. Why? Because they pop up in our formula for our Taylor or Maclaurin series. So I'm going to evaluate both of these at x equals 0. Okay, so if I put in x equals 0 here, that's just 0. And at x equals 0, for the other derivative, cosine 0 is 1, so I'm going to get something like this. Now don't worry if this looks a little bit strange to you at the start. As you do a few of these problems, you'll get more into the groove, okay? Yes? No, because minus 1 to the 2k plus 1 is always going to be minus 1. Because you're taking minus 1 to an odd power. Okay, so it's kind of counterintuitive, isn't it? It's a little bit counterintuitive. Okay, so what does this mean? Well, let's go back to our Maclaurin series. So basically what we want to do is calculate this. But it's a little bit difficult in this example because we've got these sort of even and odd derivatives. Now the nice thing though is that all the even derivatives are 0, so they're not going to affect the sum at all. So we use our Maclaurin series formula to obtain the following. Now I'm going to write this out to give you a bit more of a feel for it. That sort of sigma notation is real compact, and a lot of people look at that and go, that looks weird, that looks hard. So let me write out some of the terms here, and then we can put things sort of back together if we want. So all I'm really going to do now is just write out, replace those terms with what I've calculated above. So if I look down this column, f of 0 is just 0, so that's going to be 0. F prime of 0 is 1, so that's going to be 1 times x. F double prime's 0. And I can, then F triple prime of 0 is minus 1. So what I'm going to get is the following. Now you may be thinking, what did I mess around with all that stuff in the top right-hand corner? What do I need to know these general derivatives and things like that? Well, it'll make it a lot easier if you can formulate those general derivatives. Okay, so if I wanted to collapse this bottom line down into some sort of sigma notation like we have over here, well, it'd be something like this. And now notice I've used k's over here, so I'm going to use n's over here. So you can see here I've only got odd powers in the second bottom line. And the sign changes from term to term. So I can neatly write that in this following term, or in this following series, I guess. Now, both series are okay. Probably the bottom one's better because you're covering all your bases. You don't have to keep writing out dot, 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 dot. But you should use the setup that suits you most. So questions for that particular example. Essentially, you can break the method down to just calculate the derivatives, evaluate them at the points, look for some sort of general way of writing the derivative at the point, and then apply the formula, the Taylor series or Maclaurin series formula. So, but what does it mean, though? What does it mean? What does it mean? Well, actually, our original series sine x and this function are actually the same. Believe it or not. They are the same. They're the same function. So what you are actually doing there is writing sine in terms of powers of x, which is pretty weird, right? Yeah, we'll come back to that. So that's a reasonable example that you might be asked on end session. But I spent quite a bit of time doing that question, and as you know, I always like looking for better ways, better methods. That took me about 10 or 15 minutes to solve that problem. It won't take you as long, but there's better ways. And the important thing here is that once you know one series, like a Maclaurin series, you can use that to get all sorts of other series. No calculations really required. So let me show you. Calculate the Maclaurin series for cosine x. So there's a fast way and a not so fast way for this one. Anyone suggest how we might calculate the Maclaurin series for cosine x? Yes? Absolutely. We just spent all this work calculating the Maclaurin series for sine x. What's the relationship between cosine and sine? Well, this is the derivative of that. So maybe, just maybe, I can take this and differentiate each term. Pretty good, huh? It saves you a lot of time. Saves you a lot of time. Now, I am making some assumptions there, but yeah, it can save you a lot of time. So there are two options for these kind of problems. The first one is to proceed similarly to the previous example, and you'll obtain the following. Now I won't down all the stuff here, but again it comes down to odd and even order derivatives and trying to look for a general pattern. Okay, so I won't bore you with all these calculations. So once you've got that, you can just write out your series. You get something like this. But there's a better way for my money. There's a better way. You've already done the hard work formulating the Maclaurin series for sine x. So don't let that go to waste. Use it to do something. Use it to save yourself a bit of time. So let me show you. Okay, so we know that cosine x is just the derivative of sine x. Now down in that bottom line, if I replace sine x with its Maclaurin series, I can just differentiate term by term. So all I'm going to do is differentiate that bottom right-hand corner term by term, and I'll form a new series. So if I differentiate that, I'll get 1. That's going to, so the 3's, and you can cancel off the 3 in the factorial. Not bad, huh? So I get exactly the same series that I've got up here. So yes. Now, you can save yourself a lot of time in exams if you have just know a few basic Maclaurin or Taylor series. You can do things with them. You can differentiate them. You can integrate them. You can shift them around the axis. Okay? So, I mean, most students would see this question and go, oh, okay, let's calculate all the derivatives of cosine x. Let's substitute in x equals 0. And let's just do it. Yeah, that's okay. There's nothing wrong with that. There's nothing wrong with that. But it's pretty inefficient. Okay? It's pretty inefficient. Questions? Now, I am making a huge leap here. In this solution, I'm saying that sine x is actually equal to its Maclaurin series. Now, that's not always true. For sine x and simple functions like cosine x, it is true. But we'll have a look at that in a little while. Yes? Yeah, again, that's what I'm getting at. Switching, yes, you can. So if you wanted to put, say, like if you had, what was it? If you had this and you just put d dx out there and just shift it inside, yeah, that would be fine. Okay, that would be fine. But you can't always interchange summation and derivative. You've got to have what we know as convergence. All right, any other questions? So do these questions smarter and you'll save heaps of time, Whoa. 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 Sorry, everyone. Okay. Find or calculate the Maclaurin series for log of 1 plus x. Now, by this, I mean the natural log. Now, again, there's two ways to do this question. There's two ways. There's a smart way and a not so smart way. The not so smart way would be to calculate all the derivatives. So if you want to, you can just form another table and write out your derivatives down one side and their value at 0 down the other. I'm not going to do that. I'll just give you the general setups. Okay, so it's starting to look a bit messy, but all we're really interested in is this general derivative at x equals 0. Oh, so this is for k greater than or equal to 1. Now, when I sub in x equals 0 here, I get 1 to the k, which is always 1. Now, if you apply your Maclaurin polynomial, your Maclaurin series formula, you can get the following. Okay? Obtain the following. Notice I've started the sum in the bottom right-hand corner at k equals 1. Anybody know why it's not k equals 0? Well, the reason that this sum's starting at 1 and not 0 is because the first term's going to be 0 anyway. So you're not going to, it's there, but it's just hiding, right? It's 0. Let me show you a smarter way of doing this problem. A smarter way from stuff you already know. Now, we just finished a section on series, right? Remember the geometric series. Geometric series. This special series here. We know that this special series here converges to 1 or 1 minus x when x is, small, between minus 1 and 1 actually. Can anyone suggest how we can use that information to get the Maclaurin series for log 1 plus x? We differentiated in the previous example. What have we done? We haven't integrated. Maybe we can integrate something like this and produce log 1 plus x. Now, if you integrate 1 on 1 minus x, you obviously don't get log 1 plus x. But we can adjust. We can adjust. Now, if I replace x with minus x, I get this. Now, the important thing here is that if I integrate this, I'll get this. So all I need to do is integrate both sides and I get my new series that I'm looking for. That's all it is. So if I integrate this, I get log 1 plus x. Now I'm going to ignore the absolute value signs. And I'm putting the integral sign inside the summation sign. So what I'm going to do is integrate term by term here. So that if I integrate, the k is going to go to a k plus 1, and I need to divide by the new k. Now, if you look here and here, these aren't quite the same series. But if I just relabel everything, I get it. Ah, sorry, 0. So these are powerful techniques that can enable you just to have, from basic series, get a whole lot more without going through and computing every derivative and going through and getting, you know, like spending heaps and heaps of time on it. Yes? Concept of integration, that is managed away by substituting in something like x equals 0. Okay, because you get log 1, which is just 0. That's a very good question. Was that what you're going to ask as well? Yep. Now, you can't always find a Maclaurin series for functions. Who can tell me if this is my function now, natural log of x here? What happens if I try to find the derivatives of log x at x equals 0? You can't, right? You can't differentiate log x at x equals 0. It's not even defined at x equals 0. So here, so this is f of x. So the bottom line is we cannot compute these series for functions that aren't differentiable, right? Because the series rely on derivatives. And so no, the T is silent. Yes. So no Maclaurin series. It's French. The T is silent. Sounds a bit German. So that's a couple of ways of getting good value for your effort. Now here I am going to calculate this one just straight out. You may be able to move the curve for different functions and get a new series that way. But here I'm just going to do it just plain and simple. So this is a Taylor series, so no longer a Maclaurin series. And our A is not 0, but 1 in this case. So the point that we're interested in evaluating the function and its derivatives at is the point 1. All right, so by the log function here, I mean, of course, the natural logarithm, right? Natural log. All right, so let's just go through. I am just going to break my rule here and make a little table. So we want to calculate the function and all its derivatives at 1. Okay, I can't see a pattern yet. Let's take some more derivatives. I still can't see a pattern. I don't know if you can. Let's calculate some more derivatives. All right, so here we're going to get something like this. Now notice how I've left this sort of, the bottom left-hand corner, I haven't simplified it. In some cases, it's easier not to simplify everything. Just keep out writing the multiplication or the terms or whatever you've got there, because it may give you some insight. So that's actually quite a good rule to have. Okay, so this 3 is going to come to the front and become a minus 3. So now can you see some sort of pattern? Sort of a vague pattern here. Well, let's try to collect our thoughts and see what's happening. So at x equals 1, we have the following. So I'm just going to worry about the derivatives at the point there. Now I guess the zeroth derivative at 1 is just 0. But all the other ones follow some sort of pattern. Oh, hang on. Yes, some sort of pattern here. So the pattern can be written like this. So let's go through and apply our Taylor polynomial, our Taylor series formula, and see how we fare. Oops, sorry. All right, so here it is. So in this case, the A is 1. So all we have to do is simplify this sort of coefficient here. So let's just take this and sub it in. Now, the first term is 0, so I don't need to worry about it. I can just start the sum at 1. Now, we're just about done. All we need to do is cancel off some of those factorials. So we've got k minus 1 all factorial over k factorial. So that's just going to leave us with the following. Just a k down the bottom. So when you use that method, the hardest method is not, the hardest part is not calculating these derivatives, it's coming up with this relationship here, I reckon. So any questions for that one? Now remember, it's unlikely you'll get the Taylor series formula or the representation in your exam, so you'll need to remember it somehow. Oh, come on, you've got to keep up, guys. We've only got 7 minutes left, so come on. All right, so we know how to calculate these series now. It's not that hard. You just got to be careful with looking for patterns. The next question is, well, actually, what kind of convergence do we have? What sort of convergence do we have? Do we have convergence? If you formulate this series, does it actually equal the function? Well, sometimes. So that's what we're going to talk about now. Actually being able to write sine x or something like this as a series. Now, back when we studied Taylor polynomials, Taylor's theorem said the following. If you have a function that's differentiable enough times, that function's equal to its Taylor polynomial plus a bit left over, called the remainder. In the context of series, Taylor series, Maclaurin series, we say the Taylor series converges to the function f of x if and only if the limit of this remainder goes to 0 as k goes to infinity. So imagine x is just some number. Take the limit of the remainder as k goes to infinity. Does it go to 0? One of the ways of determining this, that's showing that this holds, is the following result. And you would have seen this before when we did Taylor polynomials, but this little bit was cut off, and I cut it off for a purpose. Just suppose your function has derivatives that are all bounded by some number, m. If all the derivatives are bounded by some number, big M, then your remainder satisfies this for all x. And in particular, under these conditions, including Taylor's theorem, the series, the Taylor series, the Maclaurin series, whatever it is, converges to your function. So let's do an example and see actually how this works in practice. All right, calculate the Taylor series for this function at this point. I'm not going to do that. I'm going to talk about the interval of convergence. So this is the Taylor series. For cosine. Okay, you should check this and make sure that this is correct. I'm a little bit doubtful now. However, what we would like to do is show that our f of x has derivatives that are always less than some number in absolute value. So, if you calculate all the derivatives of cosine x, they're either going to be cosine x minus cosine x, sine x, or minus sine x. Now, the important thing here now, what do you know about cosine x and sine x? If you take the absolute values, everything's less than or equal to 1. So the function and its derivatives are bounded by some number 1. So what this means is we can apply the previous result because we have this, so big M would be 1, and we can conclude that our Taylor series for cosine x must actually converge for all x. For all x. Okay, it's the reason for all x because we can have this bound for all x, right? This is true for all real numbers x. So if you apply the previous theorem, you get the convergence. What it says is that series, assuming that start series is correct, that is actually cosine. The Taylor series for this is cosine x. All right, guys, I'll see you all tomorrow.